Thank you very much for the organizing this program in the workshop. I've been here for 4 weeks. It's been an absolute pleasure. So it's nice to follow Igor, who I think primed everybody for a lot of questions that I'll try to discuss in a somewhat different way. So I've been working on this idea of testing quantum gravity in a lab for like 6 years. And this is my attempt at summarizing sort of the state of what we know after a lot of work. So I want to focus mostly on what we're trying to do in a high level and why we're trying to do it, rather than exactly all the details. So the test really boils down to this. So I say for poets, what I just mean is pictures. I'll give a much more precise version in a second. The question we're really trying to answer is vaguely, is gravity quantum? Okay. So a better version of this question would be something like, can I take the gravitational field prepared in a quantum state, for example, superpose it in some kind of cat state or something? And equivalently, under some assumptions, you can ask, can the gravitational field be used to entangle two systems? So the sort of cartoon here for the way this has been thought about for a long time now is, imagine I have a source mass. The source mass sources some gravitational field, and I think of this whole thing as being in a quantum state. I ask questions like, can I superpose the mass and therefore superpose the field? Or could I take a test mass and have it gravitate towards this and see some entanglement generated? I think there's been some lack of precision in this question over the years, and one of my goals is to bring some precision to it. So I want to phrase this in terms of null and alternative hypotheses. And I want to emphasize that the null hypothesis is that the answer is yes, you can do this, okay? And the idea is you just argue in direct analogy with electromagnetism and the Coulomb field. However, we don't know for sure that that is the answer, and that's why you have to do the experiment. So there's a nice review we wrote. Well, sorry, I shouldn't say my own paper is nice, but what I hope is a nice review if you want to orient yourself to the basic ideas. There's something else I want to get on the table if you haven't heard this before. So it's often, romantically posed. There's this deep question about quantizing gravity. We can't do it or something like that. Okay, that's just not true. We have a very good theory of quantum gravity. Here's the action and the definition of the variables. Okay, so this is the Einstein-Hilbert action, and then there's some other terms. And all this equation means is I assume space-time is flat plus small fluctuations, and I treat the fluctuations as a quantum field. Just like I would treat the gauge field in electromagnetism, quantize it into photons, this becomes something that you quantize into gravitons. This theory is valid at energy densities until the curvature scale R becomes of order the Planck mass. Okay, that's near a singularity, for example. On a tabletop, this condition is extremely good, and the idea is that all of these quantum corrections that you think are infinite just don't matter, okay, because they're suppressed by powers of this very small parameter. So this is, in modern parlance, this is called effective field theory. Almost all field theories in nature are like this. They're valid at some energy scale range. There's old theorems that this kind of behavior is basically inevitable, by which I mean if the Einstein equation is going to arise on average, something like this has to be going on, and this is true under very simple assumptions, namely that the quantum dynamics are unitary, they're Lorentz invariant, and they satisfy a sort of space-time locality principle, which technically is called cluster decomposition. Oops, sorry. So in my view, what we're really testing in these experiments is, does one of these postulates actually break down in nature, in the gravitational sector particularly? So I'm going to go through kind of a lightning review of proposals. So I'll start by sort of just giving my take on what Igor was just talking about in gravitational radiation experiments, and then I'll move on to the tabletop world. I probably won't get to this idea of doing holographic experiments, but if anybody wants to ask, if you've heard about this, I'll be happy to give a slide. So test in gravitational radiation field. So, there's a simple question like, can I count gravitons? And Dyson analyzed this a while ago, and then, let's take the punchline from Igor's talk to be yes. Let's say it's yes, okay? And there's other ways of doing it. You can do it with high-frequency axion detectors. You can do it with some other architectures. It's not important for what I'm going to say. The question is, what does this question tell me about testing this thing? As, there was some discussion. And everything I'm about to say comes from this paper that we posted a few months ago. So the sort of precise question I want to ask is, can I do a hypothesis test? So the null hypothesis is this one I just described, where gravity is quantized perturbatively, couples to the stress energy tensor. Everything's got a hat because it's an operator. You know, everything's supposed to just be like electromagnetism. The alternative hypothesis, and this is sort of phenomenological, would be, what if gravity is just viewed as a classical random variable? So there's no hat on the graviton here, but it couples to quantized matter in the usual way. So in general, we can allow this to be some classical variable drawn from a distribution, and I'll allow us to scan over the distribution. So why am I phrasing it this way? Because I learned all this from Mandel and Wolf. So in Mandel and Wolf, there's a very nice discussion of how does this look in electromagnetism, and how does it relate to the photoelectric effect. So you can talk about the photoelectric effect. So Igor obviously was just talking about this. Imagine I have some electrons. There's a ground state and a conduction band. The photoelectric effect is I shine light on this thing and I excite discrete electrons. And if you want to ask, can I distinguish between a model where the photon is quantized or where there's just a classical electromagnetic field, a precise way of characterizing this would be to just ask, okay, what's the spectrum of photoelectron clicks on a detector? So I count these electrons and I want to say, well, I absorbed a photon. Okay. But if you calculate the rate, just in perturbation theory, for electrons to go from the ground to the conduction band, the equation you get is the same in both of these models. So this just says that the rate, excitation rate is given by detector efficiency. This is the fractional power absorbed, times an intensity, times a step function that enforces the condition that the frequency of the light or the energy of the photons is equal to the band gap in the semiconductor. In general, there's an average on this intensity, and that average is either classical or quantum. It doesn't matter. It's otherwise the same equation. So the claim here, and I think there was a lot of discussion just now, is that the fact that you observe discrete photoelectrons does not require you to quantize the electromagnetic field. And the statement here is that the same thing is true in gravity. So a harder question is, what would you have to do to prove to yourself that I did have to quantize the field? And again, there's probably lots of people here well-versed in quantum optics who are going to know this. But in the gravitational world, this was news to many people when we wrote this. You know, there are these tests of non-classicality. So a simple single-mode version of this would be, imagine I have one mode, so one momentum of the gravitational field or the electromagnetic field. I can always write its state in the coherent state basis, so these betas are just coherent states. I can always write in a Glauber-Sudarshan representation the state as some average over, sorry, some weighted sum over the coherent states, where this p of beta is a weight, which is normalized to 1. And then there's this sort of general set of results that tells you if I'm in a state where this p function is always positive, then this literally is a classical ensemble of coherent states. And I can always make a transformation in the model where I can just explain what I'm going to see in a detector classically, with some random ensemble of plane waves. On the other hand, if you have a state where p is negative somewhere, you can actually usually find some observable, some detector output function that you couldn't not explain with that classical kind of phenomenological model. So, you know, a very famous example is sub-Poisson counting statistics. So this is you have your photodetector, you're measuring the rate of clicks, and you're measuring the variance in the rate of clicks. And you ask, you know, how does the variance compare to the average rate? So, you know, typical sources will give you Poisson light, so meaning this equals this and this is 0. But a general answer with a general input state, you have that the variance is related to the average by some formula. And this formula, the idea here is that if p is positive, this right-hand side is positive, so the count rate on your detector will be Poisson or super Poisson, meaning the variance is bigger than the mean. However, quantum mechanically, you can find states where the right-hand side is negative, and so the fluctuation statistics of your photo count rate is sub-Poisson. So the idea would be, suppose you turn on a graviton detector and you see sub-Poisson noise. Well, now I know, according to this, that I could not have explained that with a classical gravitational wave. So that sounds promising. The question is, how hard would it be to do this? And the answer is it's impossible, okay? And the reason it's impossible, at least in practice, you know, at least in these simple kind of tests, is because there's a detector efficiency. So, like I said, what I'm looking to do is measure a negative quantity on this right-hand side. The problem is that the negative quantity is sitting next to a detector efficiency function. So this is, again, the fractional power absorbed in the detector. So in photodetectors, this can be an order 1 number, and I can actually do this, and it was done in the 80s. However, in a gravitational wave detector, this is an astronomically small number. So for example, you can talk about LIGO, and you can construct an analogous test with the kind of data LIGO actually has, meaning you look at the variance in the phase coming out of the detector, and you can just compare what's the intrinsic noise in the LIGO detector versus the kind of microscopic quantum mechanical noise in the gravitational wave you're interested in. And it's a similar kind of result here. So you have sort of a detector fluctuations. So in some units, let's call this 1/2, like usual kind of phase variables. And then the contribution from the gravitational signal, there's a classical one, there's a quantum one, and the difference is up to a factor of 1/2 multiplied by a detector efficiency. And in LIGO specifically, this detector efficiency is something like order 10 to the negative 20. So what you're asking is, can I see this negative 1/2 on top of, sorry, this negative 1/2 times 10 to the negative 20 compared to the 1/2, and good luck. So to me, this is a little depressing. This is not what I was hoping the answer would be, but it looks like seeing something like this, sub-vacuum fluctuations or sub-Poisson noise in a gravitational wave is just not likely to happen. So that kind of leads you to think about other tests. And so, this is a retrocausal explanation of why people are looking at tabletop tests. But now that we have that explanation, here's how they work. So these tests are of a totally different flavor. You're not looking at the radiation field at all. You're doing something on a tabletop and looking at Newtonian fields. And I think Bell inspired a lot of these kind of approaches. Somehow it's more in the philosophy of Bell tests. So here, to be a little precise again, let me give you an example of how the null and alternative hypotheses would look. So this is the same model I showed you earlier. So if I imagine that the graviton exists, it's quantized like normal. That will generate a Newtonian potential interaction at low energies. So in terms of if I have like 2 pieces of metal, psi1 and psi2 in my lab, they'll feel some effective Newtonian force, which in quantum mechanics becomes a unitary, as everybody knows, and the unitary is given by this thing. So what else could possibly happen? Okay, so the general answer has been so far in examples of this form. You imagine that in addition to the matter in your lab, gravity is somehow basically an open system in some way. So here gravity is a unitary interaction. Here gravity is encoded in some kind of slightly open systems interaction. And so, by Stein spring dilation, you can always write it like this, where there's some ancilla degree of freedom laying around. And so in general, if you want gravity to effectively appear on your masses, so sort of on average, say, it's known that you're going to have to modify the total dynamics in some way, and the only known examples are of this form, where the dynamics of just the 2 pieces of metal in your lab are affected by some kind of averaged out Newtonian potential, where one mass sees the average location of the other. To make this self-consistent, though, it's known now that you have to add some extra noise. And specifically, this is constructed by, for example, having an ancilla, which is like measuring the position and feeding back the information. I'll show you in a second. These models differ severely from these in the sense that they cannot entangle objects by construction. That's evident from this being a 1-body instead of a 2-body operator. They are also, in general, incoherent. So they have to come with some kind of intrinsic noise. And this is a pretty general result that this always has to happen. There's a series of theorems that say this. So this suggests, so what we want to do is test these. Okay. Yeah, so this is often a common question is, okay, if I do this, what does this have to do with gravitons? I didn't say anything about the gravitational field. I just wrote a potential operator. But we know that the existence of a potential operator and the existence of propagating fields are tied to each other. So in a normal quantum mechanical model, in particular one which is unitary Lorentz invariant, and then let me put in also that it has 1/r gravitational interactions, you can actually show that any such model has to have quantized gravitons, and not virtual ones, radiative ones. You have to have a process where the graviton can be emitted from your system. And this is just a statement about unitarity, or what's called the optical theorem sometimes. that the process mediated by the virtual gravitons, there has to be a corresponding one with radiative gravitons. So actually testing these assumptions, notice this doesn't directly test anything about radiative graviton. It is actually a test of the graviton. It's, however, very indirect, and it's hard to understand, how much can we test these and in what ways. So there's a nice, beautiful paper by Alessio Valencia and a bunch of people, including Bob Wald and Marcus Hasselmeyer, and there's a more precise version of this that I published a couple years ago. Okay, so what I want to show you in a little detail is how one of these alternative models would work, and then I'll show you how you can test it. So this is just blowing up this diagram and showing you a little bit of the guts. Okay, so this is an example. It really was developed by Caffrey, Milburn, and Jake Taylor, my old boss. It's called measurement and feedback gravity, for example, or we made a more modern version, which I'm actually going to give the equations for, which we called strongly incoherent gravity. Roughly, what usually happens is you imagine you have the system, so two pieces of metal, psi 1 and psi 2, and then each of these you assign some ancilla. The ancilla measures the position of the masses, takes the measurement output, and then feeds back a gravitational force sourced by a mass at that position onto the other mass. So this just implements this interaction. Or if you kind of look at the average equations of motion, it just says you can organize it so that it reproduces the Newton law on average, so in expectation value. Okay, so in other words, this model is capable of predicting for you something like apples fall from trees, planets orbit stars, and so forth. And the only place where it will differ is once you start getting into the really quantum mechanical regime of your systems. I want to emphasize that this kind of a model usually has some free parameters. So in this particular incarnation, there's a measurement strength, and there's a rate of the measurements. So that's a V and a sigma, we call them, okay? And so what you're doing when you're doing tests of this is you really have a parameter space. It's just like a particle physics example, okay? Where there's some amount of, the parameters can in theory be anything, but then there's a bunch of experiments which say that they can't actually be everything. So for example, such a model, because it's incoherent, has anomalous heating effects. And those anomalous heating effects, can't be too large because we know that objects don't just spontaneously heat at some level. And so that leads you to this sort of constrained parameter space where these boxes are already ruled out. And then your goal is to test the rest of this parameter space. Okay? So how do you test it? One way you can test it is this sort of qualitative question of can gravity entangle things? And then another way you can test it is whether this anomalous noise exists. So I wanted to sketch sort of how these experiments look, and that'll be the punchline mostly. So the entanglement tests are beautiful. This has gotten a lot of press over the years because it's a beautiful idea. I think the core idea goes back for a long time, actually, the knots at least. But there was a paper by Sugata Bose's group in 2017 that I think really made this very concrete. And since then, there's been, I don't know, maybe 20 or 30 proposals. We had one, I think Animesh had one, Igor's probably had one. I mean, there's a bunch of these sort of ideas of roughly how would you do something like this. I think there's a pretty exhaustive list as of 2021 in this paper. The question is, can I entangle two objects with a Newtonian interaction, and can I observe it? Okay. So, very cartoony. You imagine you just take two masses, you let them sit next to each other. You imagine starting them in some product state, let them evolve into the Newton interaction, and ask, do I end up in an entangled state? How do you know? You do some kind of joint measurement. Okay. So this Bose example, one reason I like to show it is because it's extremely concrete and it gives you a sense of how hard this is going to be. So their setup is a little, I don't want to say baroque, but I mean it's a little complex. So what they suggested was take NV-centered diamonds. You can think of these as just big fat neutrons. So it's a massive object with a spin that couples to the center of mass. And the proposal was take these, send them through magnetic field gradients. So they basically go through a Stern-Gerlach apparatus. You put two of these next to each other in a drop tower. So now you have these two NV centers which are split on paths falling. And as they fall, you want to look for the Newtonian interactions between the two diamonds. And specifically, you want to look for the fact that on the branches of the wave functions where they're close, they'll pick up some phase. And on the far pairs of branches, they'll pick up a different phase. So there's some differential phase that shows up in the total time evolution. So this is the joint state of the two diamonds. You know, L and R mean left and right. And the under sort of standard quantized gravity, what will happen is your initial product state will be evolved into some joint entangled state where the amount of entanglement is quantified by this phase, and the phase is just the Newton potential multiplied by time. Rather, the differential Newton potential between the two pairs of paths. So what you need to do then is do some kind of Bell measurement on the spin, or some kind of, you know, two-body correlation measurement to check is this really the state, and in particular check if I violate the Bell inequality in the state. How hard is that? Well, you need a phase that's sort of like order 1. Maybe it can be a little bit less than 1, but it can't be astronomically less than 1. How hard is that? Well, these are the numbers. Okay, so to get sort of like order 10 phase here I wrote, you can imagine nanogram scale diamonds superposed, that's what this delta x means, at a micron, separated from each other at a millimeter. The millimeter you really can't get around. This is set by the fact that you don't want Casimir forces and stuff killing you. That's fine, that's fine. This is brutal. How are you going to superpose a diamond at a micron? Okay, well, supposing you did this, the real killer to me is you're going to have to keep this alive for a second. That means that no gas can collide with it the whole second that it's falling, and so forth. You know, any decoherence will just destroy this, naively at least. So this is extremely challenging, to put it lightly. I don't think it's impossible, but I'm also not an experimentalist. Okay. You know, people have argued, but I think also very good people are very seriously working on this. And one reason is because it's extremely clear. Like, okay, you have to get there, but then the signal is there. Like, you know exactly what you're trying to get. So, you know, I'm optimistic about these as a long-termist. That said, there is some room for things that you can do between now and such an experiment. So this is an idea that Jake Taylor proposed really a long time ago, and we revisited more recently. So this is this idea of, instead of looking for the entanglement, I said that you can also just look for this anomalous noise in a more direct way. So, you know, I think I sort of said this, but roughly the idea would be you have your two massive objects. If gravity is not quantized in the usual way, it has to be non-reversible. That's a theorem by Galli, Giacomini, and Selby. And so if it's non-reversible, there's some leakage of information into some bath. Okay. So this is just an example of how you could do this. So this is a proposal we made. There was quite a lot of activity about the interpretation of this proposal. So this is a paper. There's an errata that's important, which was pointed out to us sort of by Martin Plinio's group. But I think everybody settled on the following interpretation of this. So the idea would be you take let's say a pendulum, so torsion balance or something, and I put it next to an atom interferometer, and specifically the atom interferometer we have in mind is this one that was discussed earlier, Holger Mueller's at Berkeley, where it's a lattice, so the atoms are just fixed in a location, they're not in a fountain. I'll show you a picture in a second. And the idea would be, okay, you take the atom, you superpose it into two locations, and you just kick your oscillator next to it, and you look at the gravitational signal imposed on the atoms. Okay. So in particular, what you can do is sort of typical interferometer measurements on the atoms. So you put it in superposition, you let it pick up some phase, and then you put it back. Okay. So with the pendulum source, what this means is you're going to get some time-dependent phase that oscillates with the frequency set by the oscillator. And the idea is the following. If gravity is coherent, and for simplicity, imagine there's no technical noise. I'll talk about that in a second. If there's no external noise, what would happen is, because the source is periodic, the atoms, although they'll pick up some differential phase that depends on time, that phase will periodically return to zero, okay, because the state will go back and there's no information. On the other hand, if gravity is noisy in the way I'm discussing, then this is making some kind of noisy gravitational field which is dumping on this atom. And what that means is the state of the atoms will not actually return back to their initial condition. There'll be some kind of loss of the quantum coherence of the atomic state. So what you do is you do this, and then you look for how much loss of phase contrast is there in my atom interferometer. And the idea is, okay, you pick one of these gravity models where it's noisy. You say, okay, if the atom hasn't decayed by too much, then I know that this model can't be correct because it predicts a certain amount of noise. Yeah, so we're actually going to do this. So so this is the sort of the team. So Holger's got the atom interferometer, of course. Jake Taylor is my longtime collaborator, and then we're working with these brilliant dudes at NIST who are going to build a torsion balance, and the sort of schematic of the setup is what I was just suggesting. So you imagine you have an atom interferometer. It's in a lattice, so the atoms are superposed over here. All the rest of this stuff, don't worry about it. And then you put some shield and you put a torsion balance next to the atoms. This is separated about 1 millimeter. And the idea is you want a very high Q torsion balance for the long term. You have these atoms, which Holger can currently keep coherent for about a minute. And then you're going to do the experiment I just suggested. So the Heising-Simons Foundation very generously funded this to get it moving. And so we are starting to build this. Well, we're in the depths of the design review, actually, but we will start to build this soon. So what are we trying to do, right? So the short term, the immediate goal is just start systematically excluding these kinds of noisy models. There's a longer term goal, which is if you can have some level of quantum control on the torsion pendulum, then you can actually make nicer tests which rule out just everything. We had an idea for this. There's another recent one that I think was really nice by Ludovico Lamy and Martin Plinio and some people, where, okay, I don't want to get into the details, but this is sort of the long-term goal and one reason you want a high Q oscillator. Okay, but I want to make a last comment on the philosophy here because there's been a lot of talks from like dark matter people, and I am also one of those people. So the philosophy of this, I want to be clear, is you're trying to exclude anomalous noise. So you're not really trying to discover this noise. That's a little unscientific. Of course, you actually go in and you say, is it there or not? Okay, but my prior is strongly that the graviton probably exists, and what we're trying to do is sort of get more confident about that being true. So we're not so worried about how to pick out some noise that we think we might see and compare it to technical noise. We're really trying to do the simpler thing, which is just bound the total amount of noise in the system. It's important to understand that there are really precise statements that all of these non-standard, all these non-quantized gravity models have to have noise. This is a nice theorem published this year. The real question theory-wise is there a minimum amount of noise? Okay, so in this plot you can see there's like a sort of a bottom to this plot and a top, and there's a finite parameter space. So this is not like a dark matter search where this is so-called bottomless, as we've been discussing. It's finite. You just push this up, you push this down, and you're done at some point. Okay. We don't know if that's true in general. The way that would be true is if there's a way you can prove that there's a minimum amount of noise in any such model, subject to some assumptions about what the model has to do, like reproduce gravity on average. There's a lot of partial evidence that the answer is yes, but there's still not really a good theorem for this. And in particular, in models where gravity is some Lorentz invariant system, there's very definite statements to this effect. I'm out of time, so we're hiring a postdoc. So if you know a young theorist who's ambitious and open-minded, send them to me. And yeah, my conclusions here are really just to reiterate, doing tests for quantization in the gravitational radiation field appear prohibitively challenging, I would say. I mean, you can get some kind of very conditional information as Igor was discussing, but if you're trying to ask this, like, is gravity quantized question, I just don't see it currently. The entanglement tests that people have been focusing on are very hard, but the conclusion is pretty clear. You rule out all the non-entangling models. Then there's these coherence tests, which are doable. You can start them now, and there's versions of these that kind of already existed on accident. But so far, we're not totally sure what's the ultimate output of such things. The big theory problem is, can you classify all these kinds of models? Can you prove a lower bound on how much noise there has to be if gravity is not quantized into gravitons? And the big sort of experimental / metrology problem is, what are the optimal measurement strategies for these things? So, we're starting with stuff that we've thought of, but we have not in detail optimized everything. So, this is a nice question I'd be happy to discuss with people. Thank you.
Yes. this is probably a daft question, but you started off with the idea sort of motivating this in the context of saying it's a 1/r potential, just like electromagnetism. So what's my version of a hydrogen atom in this picture? Like what's my scales, right? What's my Bohr radius? What's my whatever, right?
Yeah, good. So it would be a bound state of two gravitating objects.
Yeah.
So, you know, a binary system, right?
Yeah, so take two neutrons, right? What's the sort of energy scales and what's the size scale that I get with that?
Yeah, so basically you can just take any of the formulas you know from E&M, take alpha, and replace it by g Newton times the two masses of whatever you're looking at. So typically that means you're going to be talking about energy scales that are, so in the example of neutrons, let me think. So the neutron, it's going to be about 10 to the negative 20 squared, roughly speaking, compared to the E&M version of that. Yeah. So you'll sometimes see people say like the gravitational strength is like 10 to the negative 36, the strength of the electromagnetic coupling in the atom or something like that. That's how you calculate that.
Okay. Mariana on Zoom has a question.
Thank you for the fantastic overview. Could you elaborate a bit more what the violation of Lorentz invariance would mean for those tests, and also what it means for tests in other sectors? Because you're connecting Lorentz invariance essentially to quantization of gravity, if I understand. So if I see, for example, violation of Lorentz invariance in the photon sector, does that mean that there is a problem with quantization of photons? I'm kind of confused there.
Yeah,
so.
good. Okay, so I haven't thought much about the violation of Lorentz invariance because if that's true, I'm just going to quit physics. But what I want, so let me stick to this precise statement here, which is there's just a theorem that says I can put in all three of these assumptions and out pops the photon or the graviton in that case. And if you break any one of these, I don't know how to prove such a theorem. But you know, it's sort of like a quantitative level. If Lorentz invariance is broken at some level, I mean, you just have to argue. You have to think really hard what exactly the implications are. You know, if it's just totally violate, well, okay, yeah. So to me, what you're really mostly testing in these examples is unitarity. I mean, I think that's the sort of really clear thing we're testing, or equivalently, whether the interaction entangles.
Does that go the other way? So if you break that invariance, that you definitely don't have a pop-up?
No, I wouldn't say so. Yeah.
But it would be very interesting because there is enormous effort in testing Lorentz violation, and it would be interesting to also see what the consequences would be.
Yeah, that's right. So there is all this precision test of Lorentz invariance, and what people try to do is write down field theories usually where you allow a Lorentz violation and you look at what changes. And so typically what changes is not the spectrum. You'll still have things like photons and so forth, but you know there's just slightly different interactions with other fields. So presumably you can say things like that here, but.
So violation of Lorentz invariance in gravity sector would not mean that gravitons don't exist? So essentially, you're thinking you needed to prove this, but the reverse is not true.
Yeah, the converse of this, it's not clear what the answer is.
So can I ask a question about this pendulum experiment?
Sure.
Where it's swinging back and forth. So the idea is that somehow there is some noise due to that's fundamental to gravity. Mm-hmm. Because it's quantized, and that somehow if I complete an integer number of cycles, that noise becomes common mode to the two arms of sort of the superposition. So they basically see the same noise. So what in the system sets the correlation time of the noise that you can claim that, well, in some sense it cancels? Like, well, you know, both they basically see the same fluctuations, and therefore it cancels. I'm not quite getting that.
Okay, yeah, good. So there's a couple things to unpack there. So one thing to be clear is if gravity is quantized like the photon is, there is no noise. there would not be a noise from
Oh, I'm
that.
sorry. This is the classical case.
Yeah.
You would see additional noise.
That's yeah, exactly.
And what is the source of that noise?
Oh, good. So
like-
it depends in detail. So okay, so then you're going to open this Pandora's box of what are these models where gravity isn't quantized. And so let me focus on this example, which, because I have this cartoon up. There, what's going on is the way the gravitational interaction is mediated is you imagine like you're in a simulation run by God, and what God is doing is he's monitoring your positions, taking the information and feeding it back onto the other objects. And so the noise comes from that measurement. It comes from the measurement, and it comes from the fact that because you had a noisy measurement, the feedback operator you do is also noisy.
In this measurement, I should think of it as, in this case, a position measurement.
Yeah.
Of where I'm localized on the left.
Exactly.
In this picture.
Yeah. So that you can get some interaction where like the sort of average value of your measurement outcome sources the Newton field of the other guy. And so then your question about rates, there's a free parameter that controls how fast you do this. So you can do it in different ways in order to get the same average equations.
And so basically this becomes part of your exclusion plot.
Exactly.
In terms of what that rate is.
Exactly. Yeah. And physically, it's very physical. So either you imagine gravity operates by doing many, many measurements very quickly, yeah, and then weakly feeding it back, or very few measurements, but then a strong feedback. Yeah. And that's sort of two regimes of this plot.
Got it. Thank you. Thank you.
Thanks. So also on the non-entangling stuff, so God isn't allowed to make QND measurements of your position, presumably.
Well, I mean, yeah, if you could do that, sure. Then maybe you can get rid of some noise on one channel. That's okay. Fair.
And so the related question. So the one
usually to make a QND, you have to assume, right, that the whole Hamiltonian commutes with the position, right? But that's not gonna. Okay.
Well, we can discuss. But anyway, so is the Schrödinger-Newton model a sub-case of this?
Yeah, I think so. And so really the sort of nonlinearities are buried in this thing I just wrote abstractly as a Wiener process.
Yeah. All right, thanks.
Thanks. Just following up on that question, if you think of the classical model as some god or classical being, some experiment, some person doing measurements, then they would have a lot of freedom to choose when to measure, what to measure, and the measurement by action would all be different, depending on your model.
They actually have exactly this much freedom. Okay, because we already know it's not working like this.
But the measurement could be like, at the beginning of the universe, then that's done.
No, because you need to be able to, causally update everything as you're going.
Why does it have to be causal if it's God?
I think we have bounds on whether are you thinking of like some super deterministic kind of situation?
I mean, it's just too many degrees of freedom that you can think of in terms of a fundamental theory, right? I mean, the measurement could be a sequence, could be just one or two, it could be on observables that not necessarily the positions.
It's fair. So I think this is partly why I try to be very conservative and say we still need some kind of a classification of all of these models. But to be clear, we know a lot. So we know that gravity works on average in large objects. And we know that to very high precision it's Lorentz invariant. And I think that really constrains how wild this sort of measurement and feedback can be.
But do all these existing models assume continuous measurements, or they are a bit more general?
I think roughly. Well, they assume some kind of discretization scale, which is fast.
Okay.
Yeah.
Hi. On your second part of the talk, if I understand it correctly, I think you are constraining a very specific type or class of classical models, namely those that have this, noise, effectively.
So I'm claiming that actually there's this theorem that says all non-entangling models where the gravitational field is a degree of freedom have to have noise. I don't know if you know this paper, but it's pretty...
I know the paper, and under some assumptions, I think one can make that claim in a discrete case. But I would say, even independent of this paper, if I link it back to the first part of your talk where you said, look, you could compare two things. One is with heads and without. that is a classical model. If I use that for the second part, it would be the same. I mean, if I remove the hats, I would always also see the same signature. So I would just say that I think here in this type of tabletop test, it's a exclusion of a specific type of classical models.
Yeah. So again, this is again why I'm saying this. I mean, well, okay. So you're positing that there could be a model with no noise, right? But no one's constructed anything like that, and all of the evidence from the constructions points to the fact that there's going to be some noise.
Well, that's the model you showed in the beginning, like where you just removed hats, you didn't add any noise. So
Yeah,
that was so what you claim for the gravitational waves,
Yeah.
you could just equally apply here. And
Well,
have
we
the
know that
same-
doesn't actually work in detail, right? So this is these old theorems by Weinberg and Bolshinsky that, you know, if you directly try to do that, you can superluminally signal. You would, in fact, in the gravitational wave toy model I wrote, you actually have to add a noise term to make it really work. Yeah, it's a good point.
Okay. Any other questions? If not, I'll ask one. I think earlier on
Someone wants coffee.
Oh yeah, we still have a few more minutes, so I'm gonna sneak my question in because since you showed the slide, I was curious to ask it. You said we could ask in the Q&A about your work on holographic noise.
Oh,
and
okay.
I'd be curious to hear about that.
Yeah, cool. So I haven't published anything on this, but I often get asked about these tests. So there's this notion that you can look for noise from holography in experiments. And I just want to show how that fits into, so holography is this idea coming out of string theory that, you know, the world is actually one less dimension than it seems. And so there's been these ideas that means the noise spectrum you should observe in nature is a little different than you would think in field theory. So just to make that precise, there's been this idea sort of first proposed by Craig Hogan. There was an experiment called the holometer built to look for this at Fermilab, and a very similar variant has been revisited recently by Eric Verlin and Catherine Zurich, and there's some experiments being built to look for this variant. The idea is the following. Imagine I take LIGO, so just two objects separated by a baseline L, and I ask what's the noise in the length, okay, caused by the vacuum fluctuations of gravity. So if you quantize gravity like normal, like I've been discussing, there's a very precise answer you can calculate. This just comes from a graviton vacuum fluctuation calculation. And the answer is that the variance in the baseline in the length is proportional to the Planck length with some order 1 numbers sitting next to it. So what's been proposed in these papers is, well, what if something else happens, not just normal graviton quantization, and there's some motivation from some things that are known in holography, okay, which they've used to sort of inspire this ansatz, is the way I would say this, that the variance is actually given not by the variance, delta L squared is given by the Planck length times the baseline instead of the Planck length squared, where there's some order 1 or something frequency dependent coefficient in front of this. And so the cool thing is, if this was real, okay, so that if you look at the graviton calculation, it says that the variance is totally unobservable. If you put in the Planck length here, the Planck length is 10 to the negative 36 centimeters or something, so you know you're never going to see that kind of variance. However, if you put in this scaling, you know, with the Planck length times, say, a baseline of a kilometer, this is observable. It's something like of order delta x is of order 10 to the negative 16, which is way above what LIGO already sees, right? So how do you get out of the fact that LIGO didn't see this? Then you say, okay, well, maybe there's frequency dependence. It only happens at some scale and so forth. So I just want to put this up there that these are like 2 definite predictions. Well, this is a very definite prediction from gravitons, and then this is the idea that people are looking for. And I want to highlight that these are totally different. So if you quantize gravity like normal, you don't get this scaling. You get this scaling. And then you can ask, how does it happen? Well, a simple thing is it has to violate locality. That's one of the assumptions I showed earlier. So far, no one's seen anything like this in a concrete, like ADS-CFT or string theory calculation, but there are some attempts to do so, and I think, you know, this is still sort of an open question. Does anything like that predict such an effect? But nevertheless, I mean, it's also just something you can go look for because, you know, who knows? I mean, this isn't the only way holography could work. We're not sure. So there's some nice experiments looking for this. There's some very nice experiments looking for this. They're kind of the coolest experiments.
Okay, well, let's thank Dan again, and we can go to our break.